Hey folks, I'm Demotro. Welcome back to Combo Class. Today, I want to tell you some really cool things about what are known as Pythagorean triples, a type of number that's often associated geometrically with right triangles, but which is hidden all over math, and which we can also find geometric versions of hiding inside rectangles, inside squares, circles, and more. For example, let's say I asked a few unrelated seeming questions. Which amounts of squares could I pack together into a rectangle that has whole numbers for its sides and also has a whole number length for its diagonal? Next question, which square shapes can I form into two squares, like adding two square numbers together, where an amount of these mini dice or square faces can both be two separate squares or be combined into a single square? Next, what if I asked, which grid points on an XY coordinate plane are like a grid point in that they have a whole number for their X and Y coordinate value, but are also a whole number distance from the origin? And another question, what if we looked at the unit circle on a coordinate plane like this, the circle with its center at the origin and a radius of 1, which points are on this circle and have a rational number for their X and Y coordinates? Now, those may all seem like different questions, but secretly they're all asking us for the sets of numbers that can be Pythagorean triples. Starting with the question of which numbers can be expressed as two different squares or as one larger square, we're essentially asking, when can some whole number A squared plus a whole number B squared equal some whole number C squared? And this is the most simple algebraic way that Pythagorean triples are often described, but it's not the only way to view them. Like I noted that we could have also asked which rectangles have whole numbers for sides and have a whole number diagonal. That question is splitting a certain rectangle that had whole numbers that we'll call A and B for its sides, and a diagonal we could call C, into a right triangle. A triangle with a 90-degree angle with side lengths A, B, and C. And due to this classic Pythagorean theorem that even if we weren't using whole numbers, this equation always holds true for the sides of a right triangle, we can see that not only are the Pythagorean triples describing sums of two squares, they're also describing which right triangles can have whole numbers for sides and describing which rectangles can have a whole number diagonal and whole number sides. But what about these coordinate plane questions? Well, if I look for grid points that are exactly a whole number away from the origin, all the ones in this range won't fulfill that. This would be square root of 2 away. This one is square root of 5 away. But if I go up to something like 3 one direction and 4 another direction, a spot that has one of its X or Y coordinates plus or minus 3 and the other plus or minus 4, that will always be exactly 5 away from the origin, because it's secretly creating a right triangle that has 4 for one of its sides, 3 for another of its sides, the right angle due to the perpendicular nature of a coordinate plane, and because of the Pythagorean theorem that tells us that c squared must fit in and describe this as our side C. In this case, a 3, 4, 5 right triangle. The simplest whole number answers to this, and the smallest and in a way coolest Pythagorean triple. When looking at the coordinate plane version of this, we'll get a lot of duplicates where we could have gone 4 over and then 3 up, or I could have incorporated negative numbers. As long as I'm 3 one direction and 4 the other direction, there are 8 possible points filling that. Those will be exactly 5 away from the origin. And those are also the points that lie on a circle with radius of 5 centered at the origin. Here are some circles with their center at the origin of a coordinate plane and whole numbers for their radii, and the circles with a radius of 1, 2, 3, and 4 don't pass through any grid points, meaning any points that have a whole number for their x and y coordinate, unless you count the times where they pass one of the axes, and one of those coordinates is a 0, which would line up to what is sometimes known as a degenerate triangle that's essentially flat, or would line up to 0 squared plus something squared equals that same thing squared, which usually isn't considered a Pythagorean triple. And these 4 circles, apart from those degenerate triples, won't pass any perfect Pythagorean triples, because that would require a spot that not only had a whole number for the radius like this, but had a whole number for the x and y coordinate too. But when we get to a circle of radius 5, all of a sudden, any coordinate point that's 3 in one direction and 4 in the other direction will be on that circle, because 3 squared plus 4 squared equals 5 squared. And if we looked at which further circles past which grid points, those would line up exactly with the Pythagorean triples, with some duplicates where we get them each 8 times in a way. And if we wanted to just get like one of each of the Pythagorean triples, we could pick an 8th out of this and just look for the solutions within there, because anytime a circle passes through a non-degenerate solution, it will do it 8 different ways, and there will be one of those ways hidden within this slice. Like if we don't care what order we put the A or B in, and we're just ordering these smallest to biggest, and we don't treat a negative version of A snuck in there as any different, because that would be the same once we square it. Now that 3, 4, 5 solution actually gives us an infinite amount of solutions based on it. It's what we call a primitive Pythagorean triple, because 3, 4, and 5 don't have any factors in common. But what if I turn these into bigger numbers based on these that did have a factor in common, like doubled each of those? Well, it does work that 6 squared plus 8 squared equals 10 squared. I also could have tripled them. It's true that 9 squared plus 12 squared equals 15 squared, or multiplied any solution that I already had for an a squared plus b squared equaling c squared with integers by any whole number constant. Double it, triple it, or quadruple it, and I'll get more Pythagorean triples. But we only call the ones that have no factor in common between those 3 the primitive solutions, like 3, 4, 5, which is so efficient that in many ways we could see 6 squared plus 8 squared equals 10 squared, its older brother, as the next smallest Pythagorean triple. The next primitive solution is 5 squared plus 12 squared equals 13 squared. All of of these solutions can be viewed as points that have an integer for their x and y coordinates and for the radius of some circle they lie on as a distance from the center. And the reason circles work so well is that the equation to graph a circle with its center at the origin is that it's all the points where the x-coordinate squared plus the y-coordinate squared equals the radius of the circle squared. Very similar looking to the Pythagorean theorem. And it's true that even if we look at smaller circles, or any circle with its center at the origin on this plane, even if some points on it don't have integers for their x and y coordinates, any point on one of these circles will have the square of its x-coordinate plus the square of its y-coordinate equal the square of the radius, which is also squaring the distance from the origin. That's partially because, like how we drew a triangle that was hiding in there, any of these points can be seen as a secret right triangle with side lengths equal to an x value, a y value, and a radius value. And as we know, a right triangle should follow a squared plus b squared equals c squared. Now, what if we shrunk down all the way to the unit circle and saw which points lie on that? The circle with a radius of 1 and its center at the origin. Well, we know that any points on this circle will have an x-coordinate and y-coordinate that each range between -1 and 1, and it will have a radius of exactly 1, the distance from the center, telling us that whatever that x-coordinate is squared plus that y-coordinate squared will equal 1, which is 1 squared. Now, obviously, this circle has an infinite amount of points on it, so there's an infinite amount of pairs that can do that, but many of those pairs include irrational numbers. Like I said earlier, what if we wondered which points on the unit circle have both their x and y coordinate rational, meaning that it can be expressed as a fraction of two integers. For example, like 2/3 or 4.5, things like that are rational numbers. So are whole numbers, because those can be expressed as themselves over 1. Any point on this unit circle with rational coordinates will fulfill some fraction, we'll call it a over n squared, plus some other fraction, we'll call it b over n squared, equaling 1. Now, it turns out the same way that I could double or triple one of these solutions to get more Pythagorean triples, if I no longer cared if I was generating whole numbers, I could multiply or divide these by any constant number. Like, it turns out, if I want to make this 3 squared plus 4 squared equals 5 squared look more like that form, then I can divide by 5 and miraculously get the true statement also that 3/5 squared plus 4/5 squared equals 1. In fact, if I took this one similarly and took out a 13, it's miraculously true that 5/13 squared plus 12/13 squared equals 1. And that means that these describe rational pairs on the unit circle. When x is 3/5 and y is 4/5, or vice versa, that will lie exactly 1 from the origin. When one of them is 5/13 and the other is 12/13, it will also lie exactly 1 from the origin. And if we only care about having all of the Pythagorean triples in ascending order and the sign doesn't matter, then we can look at that little sector of the unit circle, that little 1/8 of the pi, and all of the rational coordinate points on there can be expanded into a Pythagorean triple. This will just give us the primitive solutions, but of course, as we've seen, if I overexpand expand it. We could turn it into the doubled version or tripled version, and those will be answers as well. Now, if you just wanted to calculate algebraically what are all of the primitive Pythagorean triples so that I can then multiply them by whole number constants and get all of the Pythagorean triples, well, even the algebraic ways of deriving these, of which there are many, a few of which I'll show on the screen here, are geometric in ways. Many of them form a tree of sorts. And this tree has a very threeven structure, where many ways to create all the primitive Pythagorean triples begin with the 3, 4, 5 combination, sprout that out into 3 more primitive Pythagorean triples, each of which generate 3 more, and 3 more, leaving us with a power of 3 amount at each stage, and slowly generating all of them. And there are too many cool ways to derive Pythagorean triples for me to even fit into this episode. But that's okay, because there are other Pythagorean combinations we can talk about as well. Like, you ever heard of Pythagorean quadruplets? For some reason, every student knows about Pythagorean triples, where a squared plus b squared can equal some c squared. But almost nobody seems to know about Pythagorean quadruples, or quadruplets? Quadruples, where you have 3 different square numbers that add up perfectly into a 4th. Now, an example of that is taking a 1 squared plus a 2 squared plus another 2 squared to get us the number 3 squared. And since 1 squared plus 2 squared plus 2 squared equals 3 squared, 1, 2, 2, and 3 are considered a Pythagorean quadruple. So, are there geometric analogies for that as well, apart from just adding more amounts of squares together? Well, here we have something reminiscent of that circles formula again. Of the circle formula again, but now we have more. Closer to the formula of a sphere. A sphere. Something 3D. And it's true that we can visualize Pythagorean quadruples similar to a triple being a 2-dimensional distance with a particular radius we've picked as a 3-dimensional distance. The fact that 1 squared plus 2 squared plus 2 squared equals 3 squared tells me that looking at these now, not just as squares, but as cubes, that if I take a 1 by 2 by 2 prism, and I look at the full diagonal from that corner there, all the way to that corner over there, the full diagonal, all the way 3-dimensionally cutting through it, that's guaranteed to be exactly 3. Because Pythagorean quadruples are essentially describing whole number solutions to a 3-dimensional distance equation, just like this was a 2-dimensional distance equation of sorts. And it's even true that if I want to know the distance between 2 points in an arbitrary amount of dimensions, I can calculate the square root to get the distance of however many dimensions there were, each with their coordinates squared and added up. And yep, that means that there are also Pythagorean quintuples and onward. Pythagorean triples are the most majestic, simple of those that shows up all over math and will definitely make appearances in future episodes. But let's keep an eye out for their older cousins or relatives as well, the Pythagorean quadruples and such, which don't get nearly enough credit, secretly describing distance formulas, just in higher than 2 dimensions. Like Pythagorean quintuples would be in a way describing which 4-dimensional prisms can have whole numbers for all of their 4 dimensions of sides, and also a whole number for their hyperdiagonal. And similar to how on a 2D coordinate plane, a circle is all of the points where the x-coordinate squared plus the y-coordinate squared equals the radius squared, on a 3D coordinate plane, a sphere is all of the points where the square of the x-coordinate plus the square of the y-coordinate plus the square of the z-coordinate, the third axis you'd need, equals the radius squared. Although it's in the 3rd dimension, we don't actually have a cube for any of those powers. We just have 3 different coordinates to square and add together. And like how that was similar to Pythagorean triples, whole number solutions to that, or the points on circles that had whole number radiuses and whole number x and y coordinates, we could see Pythagorean quadruples as the spots on spheres where the sphere had a whole number radius and all 3 of the coordinates were whole numbers. Now, I actually mostly wanted to make this little introduction to all the ways that Pythagorean triples are hiding throughout geometry, to lead into next episode that's going to go beyond Pythagorean triples, to combinations of numbers with higher powers, like cubes and 4th powers that can add together, like the story of Fermat's last theorem, and the questions that remain beyond that. Anyway, thanks for joining me for today's episode. Special thanks to all my Patreon supporters who help make this show possible, and thanks to all of you. I'll see you in the next episode for some more algebraic and geometric fun.